This is a help video for the Laplace Nodal Solutions game, Level 2. So go ahead and enter that game. Now normally, of course, you would have needed to complete the introductory tutorial under the Laplace impedance simplification game in order to prepare you for that. So we'll assume that you've already done that because that has a lot of crucial information for doing these exercises. Now it's also a great idea to look at some examples before you begin trying to solve a problem. However, in the interest of time here, I'm going to skip straight into the problem at level 2. So here we have a typical problem. This has a couple of resistors, capacitor, inductor, and a sought current, all in the time domain. And we have sources with the current source that actually has an exponential function of time, and then a step function voltage source. So our first task is going to be to convert this time domain circuit, where we have farads and henries and time, into a Laplace domain circuit, where we will have only ohms and functions of S, and time will not be present. So let's do the voltage source first. That's 2u of t, so that will become 2 over S. And hopefully that Laplace transform is already familiar to you, but if you do need the Laplace transform table, you can bring that up at any time by clicking on that button for reference. Okay, the current source now is an exponential function, so we'll remember that that's 6 over the quantity S plus 10. And then for the capacitor, the impedance is 1 over SC, so that will be 1 over the quantity 3S. Again, the parentheses are crucial here in all cases to make sure that we get everything in the denominator that should be there, both in these two entries, for example. And then for the inductor, the 9 Henry will become just S times L, which is therefore 9S as the impedance. So now that we're done entering those impedances, we'll click Done Converting to the Laplace domain to check that. It is correct here. And so the next step here is going to be to, since we're doing a nodal analysis, to select the reference node. And remember that in general we want to pick a node for nodal analysis that is connected to as many voltage sources as possible, which in this case would be V1S. And we also want to be connected to as many other possible elements as we can. So the one here on the left and top would be better than the one on the bottom because that has only 3 elements. This one has, well, 2 other elements. This has 3 other elements. So we'll pick this one by clicking there. And then we'll click OK here. And then the problem will be redrawn with that reference node. Now we have the general instructions here about how to enter the equations. And also, again, if you need any help on the rational function syntax, that's always available from the help menu, which you can get through this button, or it's available right now if you want to see the rules for entering functions in the Laplace domain. Okay, so we'll go ahead now and write the equations for the nodal analysis here. So since we have a voltage source and we're doing nodal analysis, we know that we'll need to do a voltage constraint equation expressing the property of that voltage source. And so here it's connected between ground and node 1. So it'll just be, basically we're fixing the value of node 1. And then that will be equal to a fixed value, which is the value of that source, the V1S value, which is just 2 over S. So we need to enter that explicitly into the box. Again, you can't type something like V1S here. You have to put the actual value in the Laplace domain. Then we basically check that equation, and that is correct. And then, having done all the voltage constraint equations, since there's only one voltage source, now we'll go to the core equations for a nodal analysis, which are, of course, the Kirchhoff's current law equations, since nodal analysis is based on a systematic application of KCL. So now looking at the 2 nodes that we have, node 1, we notice that we cannot write a KCL equation for that because it is connected to a voltage source whose current is whatever it needs to be, therefore we don't know it at this point. So that's impossible, but we already have a constraint equation for that node anyway. So we're going to focus only on node 2. We see that there it's connected to 5 elements, none of which is a voltage source, so therefore we can select that one correctly as a node for a KCL equation. So we'll select that one. And now we're going to have 5 different currents exiting this node, or entering if you prefer. I'm going to do exiting. So one is through a current source, so that will be a fixed current value here in the Laplace domain, so we'll pick that term. Then we have 2 of these elements are connected to ground on one side, so that will require the single node voltage divided by an impedance, so we'll get a couple of those terms. And then the other 2 elements are connected between node 2 and a different node, so there we'll need a difference in node voltages divided by an impedance, and that's all going to be equal to 0. So now we'll go ahead and fill in the blanks. So this would be, actually because it's pointing into the node, we want, or at least I want to add currents going out. Now you can also add currents to enter the node if you prefer, but I just usually do it going out. It'll accept it either way. So that would be negative, and then the value of I1s would be the 6 over s plus 10, which again I need to type explicitly, 6 over parentheses s plus 10. And again, the parentheses there are crucial to keep the entire s plus 10 factor in the denominator. Otherwise it would just be the s in the denominator, and that would be incorrect. Secondly, we'll do the current through the capacitor, so that's going to be the V2. And again, I can use the tab key to quickly go to those text boxes. And that's going to be 1 over the quantity 3s. Again, parentheses being crucial there to keep both the 3 and the s in the denominator. Then for the 4 ohm, we'll have again the V2 divided by just the 4 ohms. And then for the other 4 ohm resistor, we have V2 minus V1 divided by that 4 ohms. And finally, for the inductor, we have the same V2 minus V1 divided now by the inductive impedance, which is just the 9s ohms. So that should complete that equation. So we'll check that one. Okay, and now we've done all the KCL equations, and of course you can also do things like, well, if you need to give up on a problem, you can always do that without penalty and get a new problem, and you can also access, of course, the video help that you're looking at now, or the help through the menu. Okay, so now we're going to select the remaining equation, which is the sought current equation, or sought branch current equation, and that's this current going up through the 9s ohm inductor, or impedance. So we have I naught equals, and then we need a difference of node voltages since neither end is connected to ground here. So that will be V1 minus V2 divided by the impedance, which is just the 9s ohms. And here we don't need parentheses because this has its own text box for the denominator, so that'll all automatically be in the denominator. You can include them if you want, but it's not necessary. Okay, so we'll check that equation. And now we'll check if we have enough equations. So we have 2 unknowns, namely V1 and V2, not counting the sought variable. And we have 2 equations in those variables, so that's sufficient. The sought variable is extra. So now we just type, or click rather, no more equations. And now it'll tell us that we need to basically combine these coefficients into a simplified form. And we could clear fractions if we wanted to, although that's rather complicated in this case, so I don't think I'll probably bother. But we'll do that for everything except the sought variable equations. Okay, so for the V1 equation, that's quite simple. We just need 1 times V1, and then the default 0 times V2, and that value on the constant side is just going to be the 2 over s. And now we have to put this into standard form. So let's do that on paper here. So I've worked that out over here. And so to do that, we first of all will take this term, which is sort of the constant term, the only one that doesn't involve V2 or V1, and we'll put that on the right-hand side of the equation to put it in standard form. Now it does, of course, include the s variable, but that doesn't count as a variable for this analysis because our variables are V1 and V2. So that goes on the right-hand side, 6 over s plus 10. Then we look for the coefficients of V1. So we have, for example, minus V1 over 4. So I've included that here, and I factored out the minus sign. And then we also have minus V1 over 9s. And once again, because of the minus sign, I just pulled that out front and wrote 1 over 9s. Then for V2, we look at its coefficient. So here we have basically the 1 over 3s in the denominator gives us a 3s in the numerator, and therefore we have 3s V2, so that's this term here. Then we have a 1/4, so that would be, for example, this term. Then we have another 1/4, so I wrote that over here. And then finally, we have 1 over 9s, so that would be this term. So now we have all of the coefficients of V2. And that completes that. Then we can notice that because we do have 1/4 plus 1/4, we can just cross out one of those and make this a 1/2 to simplify it, which of course you always want to do. Okay, so now before we can enter this into the equation here, we need to put this into standard form, which means we have to have rational functions for each coefficient. So here we'll put these over a common denominator. So the common denominator here, we have the prime factors are 2 times 2 times 3 times 3 times s. So that will simply, since there's no common prime factors there, we have to just use the full 36s. So we'll multiply here by 9s over 9s, and that'll give us a 9s in the numerator and the common denominator of 36s. Here we multiply by 4 over 4. That'll give us a 4 in the denominator and then the same common denominator. So then we can check that easily by just observing that 9s over 36s is indeed 1/4, and 4 over 36s is indeed 1 over 9s. Then we do the same thing over here for the coefficients of V2. So we observe here we have a 2 and a 9s in the denominator. So that'll be 18s altogether since there's no common factors there. So now we multiply this first one by 9s over 9s. So that just gives us a 9s here. Multiply this by the 2 over 2, and that gives us a 2 in the numerator. And then the 3s has to be multiplied by the full 18s since it doesn't have a denominator, and 18 times 3 is 54, and then s times s is s squared. So we have that numerator. And once again, you can check 9s over 18s is 1/2, 2 over 18s is 1 over 9s, and 54s squared over 18s is indeed 3s. And that's equal still to the same constant term. And now I just rewrote it in the next line here, just putting this polynomial in the proper order from descending powers of s, so that can be accepted directly into Circuit Tutor. And then of course the V1 term we already knew was 2 over s. So now we'll go ahead and enter these coefficients into the equation. So the V1 coefficient here, I'm going to write the negative sign out front and then just use parentheses here. So 9s plus 4. And close the parenthesis. Again, that has to be in parentheses, otherwise we wouldn't be dividing by the entire numerator. Then put the division sign, and then again parentheses 36s. And once again, if we omitted those parentheses, we'd be dividing by 36 and multiplying by s, which is not correct. So we have to make sure we have all the relevant parentheses. Then the next term, we'll type there just parentheses 54s squared, using the caret for the square, plus 9s plus 2. All of that now over, again, parentheses 18s, which again, parentheses are always essential there. And then the right-hand side is going to be the 6 over s plus 10. Once again, using parentheses. Okay, so that should be all the relevant equations we need, so we'll check those. And I should have pointed out also perhaps that it's also a good idea to actually check what we're going to really need here. Here we're going to need both V1 and V2, so we do need to enter all these equations. We could have otherwise maybe skipped to the final answer if we only need one of them, but we didn't. That's not going to help in this problem, so I didn't do that. Okay, now those have been printed out here for us. And now we simply need to copy these into the matrix equation, and we can do that most easily just by clicking the copy button. It'll do it for us, and then we can just check that equation. And you could have cleared fractions again if you wanted to, but I just didn't do that here. Okay, so now it's giving us the instructions to basically do the work on paper and preserve that. So now here's the form in which to enter the values from this. Again, I'm not going to use the matrix, and I don't really recommend using that. It's usually simpler just to use direct substitution. So our V1, we already know that, it's just 2 over s. from the original equation up here. And then the V2, now we're going to have to work that out. This is the hard part, is solving the system of equations. So we're going to come back over here onto paper again. And so basically I have these equations here. And this is fairly simple because we already know one variable. So we'll simply substitute the 2 over s in place of V1 here. And when we do that, we notice that the 2 is going to cancel with 36 to give us 18 in the denominator, and then the s will just give us s squared. So that term then it no longer contains any variable, so I can put it over to the right-hand side. So we're going to have 6 over s plus 10 plus that term now, including the V1 value. So that'll be the 9s plus 4 over 18s squared, as I mentioned, because of the substitution of 2 over s. And then to solve for V2, since everything else is on the right-hand side, we just multiply by the reciprocal of this value, cross multiply. And so that'll give us 18s here divided by the 54, etc., denominator there. And now, again, to get a simplified form of this, it is necessary to put the fractions over a common denominator, as we always have to do. So here we see our common denominator will be 18s squared multiplied by the factor s plus 10, since there's nothing in common there. So here we multiply by 18s squared over 18s squared. So the 18 times 6 is 108, the s squared. And then here we have to multiply this term by s plus 10 over s plus 10. So that will give me s plus 10 times the 9s plus 4 divided by now the common denominator, which again is the product of these two things. So the 18s squared times s plus 10. Now we can notice that here we have an 18s and here we have an 18s squared. So clearly that can and should be canceled at the earliest opportunity. So we'll cross that out and cross out everything but one factor of s here, which will help to simplify. Now, we further, to put this into a proper rational function, we need to simplify the result into a single polynomial, which now it's a sum of terms that won't be accepted by Circuit Tutor. So we'll basically distribute this out so that we can combine the two terms. And here, so we have 108s squared. Here, from s times 9s, that'll be 9s squared. So 108 plus 9 is 117s squared. Then cross multiplying here, we'll have 9s times 10 is 90s, and then another 4s from the other term gives us 94s. And then the product of the constants, the 10 times 4 is just 40. Then we have the common denominator here, which is the s times the s that's left, times the s plus 10 times the quadratic term here. Okay, so that's our simplified form, and now we can go ahead and enter that into Circuit Tutor. So again, using parentheses, that's going to be the 117s squared plus 94s plus 40, all divided by, again, now I need to actually use square brackets since we have a product of multiple terms in parentheses. We're not allowed to put parentheses inside parentheses in most cases. So here I'll use a square bracket to surround the parentheses. So sorry, first we just have s, we don't need a parenthesis for that, and then times s plus 10 in parentheses, and then the 54s squared plus 9s, plus 2. And then we close these square brackets in the denominator, and that is now an acceptable form. And just proofread quickly, and that looks like that's correct. So now we'll check these answers. Okay, so that is correct. It's been printed on the screen. And now it tells us that the next step is to use the SOT variable equation to calculate our SOT variable, which is I0. And also it's going to notify us that at this point, because we're going to do partial fractions on this I0 to get our final answer in the time domain, that we do need to factor all the quadratic terms in both the numerator and the denominator. The denominator is necessary for partial fractions. The numerator, really, we're just doing that to see if anything can be canceled between the numerator and denominator, because if that can be done, it needs to be done before we do partial fractions. So now we need to go ahead and compute this, and so we use our formula here. I0 is V1 minus V2 over 9s, and we'll simply substitute in the V1, remember, was 2 over s, so we'll put the 2 here, and then I'm keeping the 9s outside, and I'm going to put this s, since that's in the other term as well, here I'm just going to factor that out into 9s squared. So we'll just be left with a 2 here for the v1. And then we subtract the v2. So that's the 117s squared plus 94, etc. Divided by, now the s is outside, so we just have s plus 10 times the quadratic term in the brackets. So once again, we need to put this over a common denominator. Pretty recurring theme here. This is going to be a little bit complicated. So here we see our common denominator is just going to be this, basically. And so we have to multiply the 2 times this entire thing. And in order to be able to combine it with the numerator here, we're going to have to multiply all that out. So we'll have a 2 times s times 54s squared. That'll give us 108 s cubed. And then I'll take the s, I'm doing the s terms first, so we'll do the s times 9s, so that'll give us 18s squared with the 2. So that'll be this term. And then the s times the 2 times another 2 is going to be 4s here. And then we start doing the terms involving 10, so that'll be 540 times 2 is 1080 times the s squared. And then the 9s times 10 is 90s, times the 2 is 180s. And then the 2 times 10 is 20, times 2 is 40, is the constant. So those are the 6 terms from this, and then we have to subtract off these 3 terms in the numerator. So we subtract 117s squared, 94s, and the 40. Okay, so now we've got plenty of terms here. So the 40 and the minus 40 fortunately cancel out. And that's great because that gets rid of all the constant terms, which means we won't actually have to be working with a cubic term here because we can factor out an s and cancel it with the denominator. Now, basically we want to collect terms and simplify things. So I'll just put the 9s squared in here, so we have that denominator. And then here we have the s cubed. We only have this term, 108s cubed. For the s squared, we have 18 plus 1080 minus 117. Those are all s squared terms, so that works out on a calculator to 981 s squared. Then for the s terms, we have 4s plus 180 minus 94, so that works out to be 90s. And then the denominator. And further, in order to have this be accepted, we need to get rid of any common constants. So here, we can observe that all 3 numbers in the top are divisible by 9, so we can simplify that to 12, and also one of the s's cancels out of every term. So we get rid of the 9 in the denominator and have just 12s squared plus 109s plus 10. So dividing this by s, or basically by 9s, we leave an s in the denominator along with the other terms. So that's now simplified, but in preparation, again, we did have to do the factoring of both the quadratics in the numerator and denominator. So to prepare for that, I'm going to make the highest power of s squared be 1 in both cases, which will make the factoring a little bit easier. So here I'm going to factor 12 out of the numerator. So we have 12 there times the s squared, and then 109 divided by 12 is 9.083, and the 10 divided by 12 is 56, or 0.8333. And notice I'm using 4 significant digits here just for the sake of accuracy, which is probably a good idea. And again, it's the significant digits that matters, not the number of digits after the decimal point. That's irrelevant here, generally when we're going to be multiplying and dividing. Okay, and then in the denominator, I'm going to factor out a 54. So we'll have 54s times the s plus 10, and then here this will be s squared, and then 9 divided by 54 is 1/6, or 0.1667 times the s, and then the 2 over 54 is 1/27, or 0.03704, roughly, again to 4 significant digits. And so now we have this in a convenient form, and now we have to factor both the numerator and the denominator in view of possible cancellations. Although that's not going to happen here, but we don't really know that until we do it. So here we're going to use the standard quadratic formula for the form ax squared plus bx plus c equals 0. Again, as we've probably discussed before, the preferred form of the quadratic formula is negative b over 2a plus or minus the square root of b over 2a quantity squared minus c over a. That is more convenient usually than the form they taught you in high school. So here for the numerator, we're going to have the negative b over 2a is just going to be this divided by 2, which is negative 4.542. plus or minus the square root of that same thing squared minus the c, and the a is 1 already, so it's 0.83333. And then just evaluating that, again, to 4 significant digits, those two values work out to be negative 0.09269 and negative 8.991. Both of those are going to be in inverse seconds. Then factoring the denominator similarly, we have the negative b over 2a is just going to be this, and then that's going to be, again, squared inside the square root, and subtract off the c over a, which in this case is just this constant. And this time we notice the discriminant is actually negative, so we're going to get a pair of complex conjugate roots rather than real roots for the denominator. And so working the math there on a calculator, that will give us in rectangular form minus 0.0833, actually maybe put another 3 there for accuracy, plus or minus j 0.1735 inverse seconds. So now we have to write out the factored form explicitly. So the 12/54, that's the same as basically 2/9 if it's simplified, dividing by 6, and so that's 0.2222. Then we write this in factored form as s, and remember that since the root here is negative, we have to add that value, the s plus 0.09269, because if we put this in here, we want to get 0, right? That's what makes it a root. If we subtract it here, that would be incorrect. And then the same thing here, because this is negative, this is going to be s plus that value to make sure it's actually a root. Now, if you had not normalized to make the a value, that is the coefficient of s squared, be 1, then you would also have to introduce that a into your factored form. Otherwise, again, the product of the s's wouldn't give you what you had. In this case, it's okay because that factor was already 1. Okay, so then the denominator, same thing. We have again, the constant is gone, so we have s times s plus 10. And then here, since these are the roots, we have to take the negative of this, so s plus 0.0833 minus, for the first one, the j 0.1735. And then the second root will be just the complex conjugate of that, so it's going to be s, again, plus this, but now for the lower sign here, we're going to add that j 0.1735. Okay, and that's basically the form. Now, notice we can already notice the type of damping we're going to have in the circuit for the natural response. Because we have a complex conjugate pair of roots, you may remember that means we're going to be underdamped. So we're going to have an underdamped type of exponentially damped sinusoid in the solution, okay, for the natural solution. Okay, so now we're just going to go ahead and enter the value here. So that's going to be 0. Or actually, I'll just type 2/9, I think, because that's easier, and it will convert that to a decimal after we enter it. So that's times s plus 0.09269 times s in parentheses plus 8.991, close parentheses. And then we don't need a bracket in the top because that's all already compliant with order of operations. So in the denominator, we're going to have to put a square bracket so we can enclose multiple terms. Again, so we have now an s times parentheses s plus 10 times the s plus 0.833 minus j 0.1735, close parentheses, and then the same thing with the change in the sign of j. So this is now plus j times that same value, 0.735. And then we have to close the square bracket to complete that. So everything's matched. And I'll just quickly proofread that so I don't waste an attempt here. And that looks correct. And now I'm going to click check answers. And that is indeed correct. And it's been printed on the screen. And now the next step is going to be actually to do the partial fraction expansion in the Laplace domain. Okay, so in order to do that, we select the partial fraction expansion term type, and we'll have to do that on paper before we try to enter it into Circuit Tutor. So here is the unexpanded version, and in the partial fractions expansion, we're going to have a term for each of the separate terms in the denominator. So we have, I'll call it A over S plus B over S plus 10, and then for this term, I'm going to call that C. And notice that that's the term, I'm calling that C because this is the term that has the form S plus alpha minus J beta, which is the one that you want to associate with C for purposes of doing the inverse transform, which I'm already anticipating. The other term involves the S plus 0.0833 plus, and that's the S plus alpha plus J beta. So its coefficient will be the complex conjugate of this, but this is the one we're going to label C. And this is C conjugate. It's important not to mix those two up and put the C conjugate over here, for example, because if we did that, we'd get the wrong phase angle, the negative of the correct angle, and that would give us the wrong answer. So now we're going to evaluate our three coefficients A, B, and C. We don't really need to do this one because it's just the complex conjugate of this. And we use the heave-aside method, or the cover-up method, if you like, basically multiplying everything here to get A. We'll multiply everything by S, which puts an S in the numerator of all three of these. Then we set S equal to 0, which wipes out these three terms and leaves us with nothing but nothing but A on this side. And on the other side here, it cancels out the S, and now we just set S equal to 0 in each of these terms. So we have the constant, the 0.2222, and then here the S goes away. So in each of these terms, the S simply goes away, and we just have the constants that were left. So we have the 10 here, and then this complex number. But actually what I've really done here is I've used the unfactored form here, which is more convenient when you're putting in this value, because then we could just set these first two equal to 0 and just have the 0.03704 and read that off. Makes it makes the numerical calculations a little easier to avoid the complex numbers where we can. And then we just put that in the calculator, and that works out to be almost exactly 0.5. Then to find B, we multiply through by S plus 10, so that puts that in the numerator of each of these terms and cancels out the term here. And then we set S equal to minus 10 to basically make each of these terms go away, so we have nothing but B on the right-hand side. And the left-hand side, we get rid of this term, and we set S equal to minus 10 in each of these remaining terms. So we've done that here. We have the constant, then we have minus 10 in place of S, and here again, minus 10 in place of S, keeping the other constants, and then S, this term is just minus 10. This term's gone, and then here, I again use the unfactored form. That's a little bit easier here. So I have negative 10 quantity squared plus the 0.1667 times negative 10 plus that. And then, again, we could just use real arithmetic, which is a little bit faster to evaluate that. And again, keeping, even though it's a small number, we want to make sure we still keep 4 significant digits. Otherwise, we might not have sufficient accuracy in the end. We certainly wouldn't want to lose credit for all of our hard work here by leaving off some of the digits. So make sure you've got enough digits to avoid any issues with rounding error. Okay, and then for C, we do a very similar thing. Now we have to use the factored form because of the complex number here. So we'll multiply through by this denominator and set S equal to the negative of that, which will basically, again, wipe out all of these other terms, leaving us with only a C on the right-hand side. So over here, we're going to wipe out this term because it's going to cancel due to the multiplication with that. And then we set S equal to minus 0.0833 plus J 0.1735. And we do that in each of the remaining terms. So we have the 0.2222, and then here we have our S value that I just said, plus the constant. And then here we have the same S value plus the different constant. And then for the S term, we just have that value of S, the S plus 10, same value of S plus 10. And then finally, this term is gone, so we just have this value, same value of S plus these constants. And when we do that, we'll also notice that the real constants here cancel out, and we just basically are left with this. And so now if we just put that all into a calculator that's capable of doing complex numbers, that will evaluate quite easily. In polar form, we get this. However, for Circuit Tutor, we need to enter it first in rectangular form. We'll need this later, so it's good to write down both of those forms, so we have those. Okay, so now we'll select the I naught of S equals, and we're going to have a total of 4 terms in this expansion, as you see. So we need to click on this 4 times, or drag it if it doesn't work. And then these are all going to be values of current, so they're all going to be in amperes. So I'll click on the unit selection there and make that amps in each case. And then the first term is just the 0.5, and that's over S. And then the second term, the B term, is, well, I'll put the minus sign out front, I guess. It doesn't really matter, but I can do that. And then 0.002259, make sure we got all the correct digits. And that'll be the S plus 10. And again, we don't need parentheses in this case because we have separate text boxes for the denominator. And then for the C value, that's going to be, again, we have to put that in rectangular form. These text boxes don't currently allow for the polar form. So that's going to be negative 2489 minus J times 558. And then that's going to be the S plus 0.0833 minus J 0.1735. Okay, and then we can probably save ourselves a little time by just cutting and pasting this over to here and this over to here. And then I can just change the J to minus J here. So this goes from minus to plus, sort of retyping the whole thing, and then this will go from some minus to plus to make the complex conjugates here that we have in this term. Okay, so that's all of our 4 terms. Now we just click check equation. And that is correct. And okay, so that's been printed now on the bottom of the screen. We scroll down there. So now we've entered all the partial fraction equations, so we just need to click no more equations. And it tells us now we have to do the inverse transform. And we're also provided with a table, which we might need in this case. And we'll scroll down here. Okay, so we're going to, there's our partial fraction expansion for reference, and we're going to select the inverse transform. And it also points out that we have 2 sets of terms here for the inverse transform, which we might need in some cases. So I'll just illustrate that by switching over to that. So we have a power law of t and then the pure cosine function there if we need them, which we won't in this problem, but we might in some. Okay, so I naught of t equals, and now we're going to need to have a u of t multiplying basically everything in our final answer. So we'll enclose everything in brackets to make that easier. And then we don't have any constant term, as you see here. There's no constant. So, oh, I'm sorry. We do have a constant. We have the 0.5. Take that back. We have a constant. And then here we have, that's going to be an exponential term, as you may remember. So that's going to be this type of term. And then for this, that's a complex conjugate pair of poles. So that's going to yield us the exponentially damped trig function. And it reminds us that we have to have the prefactor of that be positive, and don't try to do any funny games with minus signs there because it won't work for cosine. Okay, and then we put our closing bracket and our u of t function. Now, again, if you didn't know or remember that that was what you have, you could scroll down to the bottom here and look that up. Here's the form that we were using for these 2 terms, and here it's called k, but and it's showing here in polar form, so that's why we need the polar form of that c constant. And then this is the inverse transform. So now to compute this inverse transform, we'll take 2 times that magnitude, which is the 0.519. And so I'll go ahead and just put that in. So let's see, let me get rid of my table here. And that's going to be 1.52, so that's going to be 1.04 roughly. I'll just check that since I didn't do that arithmetic. Yes, so 1.039 to be a little more precise. 1.04 is good enough. And we know the exponential is going to be a decaying exponential, so that has to have a minus sign there always. And now we need our time constant, which is basically going to be the reciprocal of the alpha. So remember, based on that formula that we were just looking at, we have s plus alpha minus j beta. So our alpha is the 0.0833, and that's going to be the reciprocal of that is going to be our time constant. Remember, that's inverse seconds, so its reciprocal is 12 seconds to put it in the denominator. Since this form is not e to the minus at, it's e to the negative t over tau, basically. And then our beta is the angular frequency here. So the beta is going to be the 0.1735 that we had there. So 0.1735. And our phase angle is that of the c constant here, which is negative 118.6. That's why we need this polar form. So I'm going to make that a negative, and then a 118.6. And be sure when you compute that, by the way, that you use the rectangular to polar form, or function rather, on your calculator. If you didn't, you might use an arctangent, you'd probably get it in the wrong quadrant. So you have to notice here that the real part was negative, so that puts it over in the, you can visualize that, it's going to be over in the third quadrant, not in the first quadrant. So we have that correct angle. And then here we're going to have the 0.5 for the constant term. And here for the b term, s plus 10, we're going to have our coefficient, actually I'll put a minus sign out front there. And then we have a small coefficient there, 0.002259. And then again, this has got to be a decaying exponential, so that's going to be negative. And the time constant here, we can compute for the 10 is just 1 over 10, of course, is just 0.1. And then the final units, which we also need to specify, are going to be amperes. Okay, so that should be our final inverse transform. And so we'll go ahead and check that. And indeed, that is correct there. And we can scroll down and see that's on the screen. And since we've entered all the inverse Laplace transform equations, we just click No More Equations to complete the problem. And now it'll give us the PDF transcript of your work that you can use for reviewing, and it'll show both the correct steps you took and any mistakes you might have made will be shown in red in that transcript. So that'll be available by clicking the Review Work button on the level menu. Okay, and then you have the option to view a detailed explanation, which will be done very similarly to what we did, but it might be a little bit different in terms of how the computer would solve it. And so it shows us both the conversion from the time domain to the Laplace domain, and then it shows the calculations here. It's actually normalized these functions a little bit earlier. But basically the steps are all similar to what we did, and shows the results here. And if you need explanations of any of the equations, for example, you can get them here. And you can also look at the Gaussian elimination steps, though I don't really recommend solving problems that way, but it does have an option to do that if you wish, which in this case was fairly simple. Okay. So I'm just going to go back to the main menu here, and this is where you can review your work and look at any transcripts. And that also it's going to ask for the survey, which you would normally complete. So that finishes this example.